Hello everybody. Today we are going to discuss a very interesting topic uh, which is categorized under heavy engineering segments. We'll be discussing about the design, mechanisms, simulation and processes, the manufacturing processes of a induced draft fan radial impellers. So these structures are generally made using metals, either by a casting process or by fabrication process. And these structures range from zero point 0.5 tons to about 10 tons in most of the cases. So this particular impeller, which is called as an induced draft fan radial impeller, is used in many industries, especially thermal power plants, nuclear power plants, chemical reactors, etc., etc. And a different version of these structures are also used in bigger pharmaceutical companies where there is a lot of chemical related activities taking place. So here on the screen, we have an impeller which is fabricated. The actual impeller from the client was a casted impeller and weighed almost about 1.5 tons. So the client had requested for a research study between the fabricated and the casted product. So this particular impeller is about 1.2 meter in diameter and weighs about 0.7 tons or close to 685 to 700 kgs. Now this is made using MS plates which are properly stacked and welded. So these are welded structures and completely designed for optimization. So we have taken up this particular activity as a part of the research request from the customer, where we have studied the casted product. So it was CS 245 which was used as the material, which had very good yield strength properties and thermal coefficient and linear expansion factors. So the actual product from the reputed client was kind of over designed, and that's what the customer felt was over designed for the kind of application that they were using. So that particular product worked with a rotational velocity of 600 rpm, and they in fact had upgraded it, and they had also gone up to 1200 rpm for that particular casted structure. However, the casted structure faced a lot of issues which specifically triggered the interest of a research using fabrication process. So we had designed this particular structure, and the structure what you see on the screen is an optimized structure. The product before this particular optimization was done was a bit different. where it had a central disc and a shroud on both top and bottom. So that was a completely casted system which was connected to the shaft, and this particular shaft was rotating at 600 to 700 rpm. So that was the variation, and later on they observed that the structure was heavy, and the cost was also very high, which triggered the thought of optimization. And at the same time, the client had to increase the rotation, the RPM, from 600 to 800, and then gradually to 1000, and then to 1200. So there were three categories of upgradation. And this particular structure, what you see on the screen, this is the final product after optimization. So here, these plates are all MS mild steel plates, which are properly stacked and then welded. And the structure was subjected to a rotational velocity of about 800 rpm for the first study, and then a simulation, a computer-aided engineering, a finite element analysis was performed on the structure, and the stresses and the deformations we studied. So this particular impeller has got a central disc, a top and a bottom stiffener, a top and the bottom shroud, and then a top and the bottom crown. And now there is a specific reason for the crown on this particular structure. So the initial thickness of the disc was more than 30 mm. So now here, for this particular design, the thickness was considered to be about 22 mm, and the rest 8 mm was split and equally distributed onto the top and the bottom stiffeners. Now the reason for that was, in the previous simulation, for that particular RPM, about 800 RPM, the structure, the blades, the vertical blades or the vanes, what we call, buckled. So it had experienced both bending and shear failures. So what we had done is, the main disc had been reduced, and the thickness that we had reduced from the main disc was equally distributed onto the top and the bottom stiffeners. So which means that the actual blade, the vertical blade, was stiffened on either side of the central disc. So this reduced the bending stresses which acted on the blades. And now, how does the bending stress act on the blades? So for this, we need to understand the principle behind the impeller. So there is a shaft at the center that gets bolted onto this particular hub, and the diameter of the bolts are 42 mm dia, and that shaft is inline to the axis, the vertical axis of the impeller, and that shaft rotates at about 800 rpm. And when the shaft rotates at 800 rpm, it swirls and takes a thin layer of air which is bounding the shaft, and it sucks it inside the impeller, and then it radially distributes it through the openings. These are the blades, the radial blades, and through these openings, the air which is sucked from the shaft line gets radially distributed. So now when the air enters inside, along with the shaft rotation, that has a specific amount of kinetic energy. And now this kinetic energy is radially distributed, and that completely gets converted into pressure energy. And this pressure energy is what is expelled out of the gaps. So this is the actual process of an induced draft fan radial impellers. Now this is the CAD model of the impeller that we had designed, and this model was subjected to finite element analysis. It's a mathematical interpolation, a formulation with which this particular CAD geometry, the 3D solid model of the impeller, is broken into well-defined geometries. So now, since this being a three-dimensional CAD model, 3D solid model, this will be broken into well-defined tetrahedrons. So we are considering isoparametric second order elements, tetrahedrons, for our simulation. So there are different formulations where we could go for isoparametric tetrahedrons, or we could go for brick elements, or generally called as hexahedrons, or we can also go for hybrid algorithms where we have most of the elements as hexahedrons, then we have pyramids, wedges, and tetrahedrons. So that is called a hybrid. So now, since this being our initial simulation, so we go for an automatic isoparametric tetrahedron elements. Sorry. So now we get into the analysis part, the pre-processing part, where we are breaking down this particular geometry, the 3D solid model of the impeller, into tetrahedrons. So in this process, this particular geometry is broken into well-defined tetrahedrons. So these elements, what you see here, these elements are tetrahedrons. So tetrahedrons are diamond-shaped geometry structures, and that has got 4 vertices. And now each 4 vertices will be covering a triangle to it, and then whatever physical parameters we are applying on the structure will get transmitted through these interpolated points, and that is how the integration of the system happens. Say for example, we have the force matrix. Okay, so now we have the stiffness matrix. So force matrix is equal to stiffness matrix multiplied by the displacement matrix. So F is equal to K into X, where F is the force, K is the stiffness, and X is the displacement. Now we need to find out what is the displacement. So the force matrix divided by the stiffness matrix is equal to the displacement matrix. So each element, so whatever triangular entities you see here, these are all each solid element. We call it as isoparametric tetrahedron elements, and these are well-defined geometries, and through the interpolated points we call it as nodes, and these elements are all connected using nodes. So a geometry, a triangle is connected by 3 vertices, a quadrilateral is connected by 4 vertices, a rectangle is connected by 4 vertices. So similarly, the tetrahedron element is connected with 4 elements, and now each face, each triangular face will also have a single node at the center, at the centroid. So similarly, each element is interpolated, and whatever force, the physical parameters we give as the input is converted, okay, with the geometry taking the area of each tetrahedron. The force distributed. If I apply a force of say 180 newtons, that 180 newtons will be divided into that will be distributed all across these elements. Whatever triangular elements you see here, these are not triangular because this is a solid, that will be tetrahedrons. So now force divided by the stiffness matrix will be equal to the displacement matrix. So that's the principle here. The force, instead of force, we are going to have a rotational velocity at the center of gravity of the structure. So you find a rotational arrow mark. This is nothing but the center of gravity, the rotational velocity along the center of gravity. So the central axis of the impeller we are applying, that is the shaft center is the central axis. The shaft center we are going to apply 800 rpm. So we have applied 800 rpm, okay, and this is the finite element model, and we are going to apply the boundary conditions. We know that the shaft is going to be connected to these bolts, and these are 42 mm dia. Okay, so now this should be constrained. So the constraining mechanisms, we have 3 translations and 3 rotations. So any object when it remains static at the same position, that is at the origin, it is at a state of rest which is 0. Now when this object moves, during the movement or during the path of motion, there are 3 translations and 3 rotations induced on the structure. So which means there will be a displacement taking place on the structure, and apart from the displacement, because of the friction, there could be some overturning also. So the structure can rotate or the structure can topple, which happens because of the moments. These moments are nothing but the rotations. So here we remove or we make that particular, the axial part free. The axial rotations are all freely enabled, whereas the translations and the other rotations are constrained. Okay, so now this particular shaft is getting connected to this hub, and it's bolted with a 42 mm dia bolt, and the suitable constraints are applied. Now we have the internal region, the internal disc, which also has got 2 bolt holes each, and these 2 bolt holes are to connect the plates. So as I told you earlier, the customer had a 30 mm thick structure, I mean a plate, not a plate, it was a structure, fully cast structure, and that particular dimension was 30 mm. And now we had removed certain material from that, and we have reduced, we have assumed, instead of 30 mm, we have assumed it to be about 15 mm thick, and to that 15 mm thick, we have added another 5 more mm in the form of 2 plates on top, this side, as well as the bottom side, the opposite side. So the central disc is reinforced with the 2 different plates on either side, okay, just because we wanted to stiffen that particular region, because we know that the stiffness keeps reducing towards the edges and the stiffness becomes more towards the center. So that is the reason the probability for any circular membrane or a structure to fail at the edges are more than to fail at the center. So which means the cracks, they generate from the edges, the outermost. So the cracks usually generate from this portion, and it propagates inside and it goes to the center. So that central region, we had increased the thickness by adding 2.5 mm thick plates, and we have bolted it using 22 mm dia bolts. So the internal bolt holes are all bolted using 22 mm dia thick bolts. So now this particular system is subjected to simulation. So we are giving the parameters as rotational velocity of 800 rpm, and then the bolt holes are all constrained, and then we do the analysis. So this particular study, we are going to understand what is going to be the deflection and what is going to be the stress. So after the simulation, we have the stress results. So now we know that this particular structure is about 685 plus kgs, which is almost about 0.65, 0.7 tons. And the earlier structure was about 1.25 to 1.5 tons. Okay, but was operating at a higher RPM. But then we are reducing the structural topography as well as the geometry, and by reducing the geometry, the dimensions, we are arriving at a new structure, new geometry. And this particular new geometry, whatever we have arrived at, is taking care of the physics, the requirements. So this is the stress value, and we are able to see the structure is symmetrical, and the stress patterns are also, the contours whatever you see are also symmetrical. So the region in blue is about 0.117 to 12.4 Newton per mm square. So it's considerably less because the yield strength of the material itself is about 241 Newton per mm square. So now 12 Newton per mm square is a considerably low value. So that is safer. Now let's see what is the maximum value is about 41.2 Newton per mm square. The zones with red color. So now let's try to understand, figure out where exactly the red zone comes. So the red zone comes only at a very specific region, the edges, wherever edges are there, we find the red contours. And now what it means, it's called stress linearization or general or local stresses. Now these local stresses can be eliminated by certain manufacturing process, either by providing a sharp fillets or by deburring the edges. So in this case, what we do is we try to deburr the edges. We try to create some small radius so that the stress accumulation becomes lesser, so that it doesn't become the hotspots for our simulation. And then again, the region where the central disk is connected to the blades, the vertical blades. So there again, because of localization, we find some red contours. So now we know that the overall stress value, which is the von Mises stress, is about 41 Newton per mm square, and the yield is about 241. So which means we have a higher amount of factor of safety left. So that indirectly or directly it means that the structure can be further optimized. Now let's get into the displacement point of view. So this particular structure goes through a lot of bending and shear loads. The reason because the axial load, the axial air that gets along through the shaft axis is sucked inside, and it comes out of the regions open. These were opening regions, the air comes out as pressure energy. So now that pressure is causing deflection at these blades. So the red color zone is the region that has got a higher deflection. So let's see what is the displacement here. We have 0.006, because 0.06, yeah, that is the 0.06 mm is the deflection, and here the blue region shows 0.006, which is 6 microns. It's very less. So that occurs here at the center, the hub, where the shaft and the hub joins. So as I told you, the tearing stresses are more towards the edge than the center. So that's the reason you find that the stress values at this zone is higher and the stress values at this zone is lesser. Okay, now the system says that from the stress point of view, the structure is safe, and from the displacement point of view, the structure is safe. Okay, so now what we do is we try to understand like what is the factor of safety. Now we have the yield strength of the material as 241 Newton per mm square, and the achieved stress, the von Mises stress, which is the combination of your shear stress, the bending stress, and the direct stresses. Now all three put together is the combined stress or the von Mises stress. So stress theory, there are a lot of stress theories. So you have Rankine stress theory, you have Mohr-Coulomb stress theory, you have Tozagi stress theory, you have draŌ stress theory, von Mises stress theory. See, all depending upon the type of models, the system that you are working on. So here it is a completely metal-based structure, and these are elastic in nature, and now there is absolutely no plasticity here occurring. So now these kind of structures we either go for draŌ or for von Mises. Now there are systems where we interact. We go with heterogeneous systems. We have sand, we have water. So there is a fluid and a structure interaction. You have sand, a structure, concrete, steel, and then water. So you have heterogeneous systems. So in such regions or such areas, we go for Rankines or Tozagi or Mohr-Coulomb. Okay, so these are the zones where you need to find out the bearing capacity of the soil. You need to you are driving piles into the sand, and you want to check for the pile load. So you want to perform a pile load test, and you want to understand whether the pile cap is going to be safer. And over the pile cap, you are raising a pier. You want to check the load that comes from the girder. The rolling loads, the influential loads, okay, all kinds of braking loads, the traction loads, all kinds of loads, the shock loads, everything is properly transmitted to the ground, and then all these loads are going to be distributed onto the pile. And now you want to check what is the strength in the pile, whether the pile is going to behave safer. So there the system is going to be complex, it's going to be heterogeneous. You have water, you also have soil, okay, you also have the pile is going to have reinforced concrete as well as steel. So it's a combination of steel, reinforcements, and concrete, soil, and then water. So if it is soil and water, you need to check for the bearing capacity, because there is going to be some plastic zone, okay, and then the structure can behave in a non-linear way. So there are complexities involved in such cases. So that is the reason there is a different stress theory that we follow. So now let's come back to our area. So we have designed the structure, and I told you that there is a specific reason that we have a top crown and a bottom crown. So it's basically for distributing the stress completely. So whatever stress that accumulates on the system, that can uh, distribute over the crown. And moreover, crown is a member that will be able to remove, or it will be able to stiffen the torsional loads, because here there is going to be an enormous amount of torsion induced, because the shaft is rotating, and when the shaft is rotating, there is a blob of air that is stuck inside the impeller, which is going to be radially thrown out, dispersed out. Now in that procedure there is a torque induced, and this torque is going to create a torsion on the structure, and to reduce the torsion on the structure we have the crown designed. So now we have the system is safer, and now there is a chance, there is a scope for further optimization where we can reduce the thickness of the individual members. So now, reducing the thickness of the individual members, we will be able to understand like how the structure is going to behave, whether it's going to be safer. So the stress values can be brought as high as 180 or close to 180, because we have the the stress values as 61, 62 Newton per mm square. The low values are about 12. So yeah, yeah, the here we find that the stress values are 41. Okay, so which means we can further keep reducing the thicknesses of each member, and then we will find that this value will keep increasing. It can go up to 160 or 165, and then we can stop there, because we will try to keep a a safe margin. So instead of 241, we can even go up to 180. That is not a problem. Okay, but then on the later front, when these structures are going to experience any external loadings, or if there is a influence of any other loadings on this, so that is when we need to again redesign the structure. So let us say that there is going to be a random vibration that is going to occur on the structure. So randomly, this particular structure is going to experience vibrations from yet another different system. So in such cases, we will also need to perform a natural frequency analysis, a forced frequency analysis, a random responses, and then account for the random vibrations. Now we know that the natural frequency. Okay, so when the system is experiencing, okay, there is a point where the the complete system can collapse because of resonance. So that is called the resonating frequency of a system. So that's the reason, even if the structure is going to be safer from the structural point of view, okay, when there are dynamic loadings acting on the structure, the system can fail. So many structures are there, especially the chassis of a car. Okay, the car is rotating at a very high speed, say about 1000 rpm or 2000 rpm, and there is going to, I mean, it's moving at a considerable speed, and there is going to be enormous amount of forces acting on the tire, and from the tire there is going to be impact loads acting on the suspensions. Okay, suspension will drain out some loads because it has got a spring and a damper system. So the most of the, I mean, many forces can be dampened out. Okay, tire itself being a non-linear material, that can again dampen out some part of the forces. And apart from that, the major part of the force or the impact that comes from the potholes or speed breakers, all these things are having a direct influence onto the chassis. Okay, so now such situations can occur randomly. Okay, now all those random loadings are acting on the chassis. So there is a probability for stress to accumulate. Now, in order to reduce that stress accumulation or the stress to dissipate out, there are certain holes that is provided on the chassis. So those are the zone of hotspots where the stresses need to be released out or relieved out. Okay, so that is the reason after a very long trip, the structure, I mean, the vehicle needs to be, going through a maintenance process. So during the maintenance process, the stress relieving techniques, the mechanics they perform, the stresses are relieved out of the structure. Okay, now let's wind up for today, and I would request you to kindly subscribe and share this particular video to as many people as possible, because this is supposed to be one of the most important and interesting videos, and a very simple video where people can understand, the engineers can understand how a finite element analysis has to be performed on a industrial system. What are all the things to be kept in mind? What are the processes that is going to act? So this entire video I have mentioned about the entire process of manufacturing, what was the process the client followed, and what other processes are innovated, and what other processes could be actually followed, so that most of the problems or issues, okay, that comes in the generic manufacturing process can also be avoided here. Okay, and how the optimization of the material and the cost optimization can be done. Okay, so please subscribe, share, and pass on your valuable queries. Okay, thank you very much for your valuable time, and in the very next video we will be uh, coming out with a wonderful case study, and Maybe we can have an extension of this particular case study where the computational fluid dynamic process is, I mean, the method is also adopted. So we will be studying the fluids. We will be visualizing how the air, enters inside with the shaft into the impeller, and when the rotation happens, when the impeller rotates, how these air, the kinetic energy of the air gets converted into pressure energy, and it is radially thrown out from the gap of the impeller. Okay, so that we will be able to visualize it in the next episode. Thank you very much.